We present our oral work at WACV 2026, titles, Occlusion Boundary and Depth, Mutual Enhancement via Multitask Learning. Occlusion boundary estimation and monocular depth estimation are both inherently ill-posed problems due to single-view perception ambiguity. However, both tasks capture complementary aspects of 3D scene understanding and are highly correlated. Previous works have already leveraged occlusion boundaries to refine depth estimation results. However, the joint learning of both tasks remains largely understudied, especially when considering self-occlusion-aware occlusion boundaries. Occlusion boundary estimation identifies boundaries arising from both interobject occlusions and self-occlusions within individual objects. This task is closely related to monocular depth estimation, which infers depth from a single image, since occlusion boundaries provide critical geometric cues for resolving depth ambiguities, while depth can conversely refine occlusion reasoning. The core motivation of our work is to systematically model and exploit this mutually beneficial relationship, and to propose a simple yet strong baseline that advances research on the joint learning of these two tasks. This image shows a comparison of zero-shot results on a real-world example from the IBIMS-1 dataset. Significant self-occlusion boundaries are highlighted in red. Our proposed multitask framework, MODOT, is jointly trained to predict both depth and occlusion boundaries from a single image. Compared to the single-task depth baseline, which is trained solely with depth supervision, MODOT produces more accurate and structurally consistent depth maps on unseen scenes. Particularly around OB ground truth, while adding only 11 million parameters, roughly 4% of the single-task depth baseline. Compared to the single-task OB baseline, MODOT tends to predict more occlusion boundaries, resulting in higher recall, but introduces some additional noise, leading to a slight drop in F-score. All methods are trained exclusively on our newly proposed synthetic dataset, OB-HyperSim. Our contributions can be summarized as follows. First, we systematically model and validate the mutually beneficial relationship between discrete structural prediction, occlusion boundary estimation, and continuous geometric regression, monocular depth estimation, through extensive experiments. Second, we propose MODOT, the first multitask occlusion and depth optimization training framework, which simultaneously estimates monocular depth and occlusion boundaries and notably outperforms both single-task and multitask competitors. Third, we introduce a novel loss function, the occlusion boundary depth constraint loss, or OBDCL, and a simple yet effective module, the cross-attention strip module, or CASM. Together, they systematically capture the mutual geometric correlation between long, narrow mid-level occlusion boundaries and high-amplitude depth discontinuities. Finally, we construct a photorealistic dataset, OB-HyperSim, providing pixel-perfect annotations for both depth maps and self-occlusion-aware occlusion boundaries across diverse indoor scenes. Models trained on this dataset demonstrate strong zero-shot generalization to real-world scenes. Here we present the pipeline of MODOT. On the left is the main architecture used in the first training stage. We use a SWIN transformer as the shared encoder to encode RGB inputs. For the depth decoder, we adopt the decoder from the single-task depth baseline, which employs neural window-based fully connected CRF layers to decode depth, with a pyramid pooling module aggregating global high-level context. For the OB decoder, we use simple convolutional layers with side output supervision applied at each stage. Additionally, we improve the image path from prior work by incorporating spatial and channel attention mechanisms, forming the Enhanced Image Path, or EIP, which captures local low-level image features for the final OB decoder and the subsequent refinement stage. On the right are the detailed structures of CASM, EIP, and the second stage refinement module, named SSR. The hierarchical features extracted by the shared encoder are fed separately into the depth decoder and the OB decoder. The proposed CASM is composed of two components and is designed to pay more attention to depth. First, it uses cross-channel attention to enhance OB-aware depth feature channels and depth-aware OB feature channels. Second, it employs a multi-scale strip convolution layer to deeply fuse depth and OB features, enlarging the receptive field for depth while capturing the orthogonal, elongated structure of occlusion boundaries. Overall, CASM facilitates cross-task communication between the encoder and both decoders. SSR further refines both depth and OB features at full resolution through an additional CASM and several convolutional layers. During this stage, the first stage model is frozen. The idea behind OBDCL is simple: depth values across OBs should be different. During training, in addition to the standard depth loss and OB loss, OBDCL provides an additional cross-task constraint that explicitly enforces geometric consistency between predicted depth discontinuities and OBs. Here we show qualitative examples from the synthetic OB hypersym and the real-world NYUDV2. Due to the lack of ground truth occlusion boundaries in NYUDV2, we use object contours as pseudo-occlusion boundaries to train our models. As shown, training with occlusion boundaries helps the depth model sharpen depth boundaries and also reduces texture copy artifacts. For example, see the computer in the first row. For occlusion boundary estimation, multitask learning improves recall but causes a slight drop in F-score. More qualitative results are presented in the supplementary materials. The next two slides present quantitative comparisons with single-task and multitask baselines. We evaluate our method on 2 synthetic datasets and 1 real-world dataset. For competitors, we include both CNN-based and transformer-based methods from multitask learning, as well as 2 single-task baselines. Due to internal architectural constraints regarding input shape, 2 transformer-based models performed poorly after resizing, so we only report their results on NYUDV2. In this slide, we compare MODOT with depth-only methods, specifically depth anything V1 and V2. For occlusion boundary comparison, we extract their predicted depth maps and apply edge detection to obtain coarse OB contours for evaluation. The top table shows results under different Canny thresholds applied to the depth maps. The bottom table compares depth and OB results on OB hypersym. Additional experimental settings and zero-shot results are provided in our supplementary materials. This slide presents an ablation study on depth performance with different auxiliary tasks. Joint learning consistently outperforms single-task depth estimation. And compared to jointly learning depth with other tasks such as surface normals or edges, jointly learning with self-occlusion-aware occlusion boundaries clearly yields better depth metrics across nearly all evaluation scores. Here we present a component ablation of MODOT. We gradually add each proposed module and the OBDCL loss to evaluate their individual contributions. One interesting finding is that simply jointly learning the 2 tasks, without any additional modules, already yields better performance than either single-task baseline. Additionally, we observe that using the CASM or SSR module, which is mainly composed of CASM, reduces the OB-F score while increasing OB recall. We believe this is because the model predicts more depth-related edges that are not actual occlusion boundaries. Here we present additional zero-shot results on the IBIMS and diode datasets. We outline several directions for future work. First, designing a new crosstask interaction module that improves all metrics simultaneously, since the current CASM improves OB recall but causes a slight drop in OB-F score. Second, incorporating additional tasks into the multitask framework, such as surface normal estimation and semantic segmentation. Third, extending our OB-depth joint modeling pipeline beyond indoor scenes to outdoor and in the wild scenarios. Thank you for your attention. If you find our research helpful, please consider citing our paper and starring our code repository.